Okay, so this is a problem that someone asked me in Discord where we're trying to find the number of microstates so we can find entropy for a two harmonic quantum oscillating system. One has a natural frequency omega naught and the other is 2 omega naught. So the way that we're going to do this first is just remember that for a harmonic oscillator, the energy level is h bar omega n plus 1/2. Okay? Now, for the first one, we'll just call this the first one, this the second one. E1 is just h bar omega naught n plus 1/2. And E2 is 2 h bar omega naught, and we'll call this N1 N2 plus 1/2. So the total energy will be the sum of the two, so E1 plus E2, which is equal to h bar omega naught N1 from here plus 2 h bar omega naught N2 plus 1/2 h bar omega naught plus h bar omega naught. Okay? Now we can factor this out a little bit because we can factor out an h bar omega naught here, and we're left with N1 plus 2 N2 plus 1/2 plus 1 is 3/2. 3/2 h bar omega naught. So that's our energy. And we can define a new n as being N1 plus 2 N2. So then our energy is just h bar omega naught n plus 3/2 h bar omega naught. Okay. So now what we need to do is find the number of microstates, which will be related to this. And the way that we're going to use it is combinatorics. So C and R is equal to, and I'll explain this if you're not super familiar. Okay. So the way that this works is N is the size, you could say, of the set, and R is the size of your permutation. So R is going to be 1 because we're interested in it settling into one state, and N is the number of different states that we're looking at. So N equals 1, 2, 3, what have you. So then we would say this is equal to n factorial over 1 factorial times n minus 1 factorial, which is just n factorial over n minus 1 factorial. Now, we can simplify this a little bit. So factorial, for example, n factorial is n times n minus 1 times n minus 2 times ... So n factorial is n times n minus 1 factorial. So this is n times n minus 1 factorial over n minus 1 factorial. So this is just equal to n. Okay? And this is the number of microstates, omega. These are all the different configurations of one end state, which I guess kind of makes sense, right? And our entropy is equal to KB, the natural log of omega. Okay? Well, what we can do then is, if we look at our energy equation, we can solve for n here. So E is equal to h bar omega naught n plus 3/2 h bar omega naught. So E minus 3/2 h bar omega naught equals h bar omega naught n, or E over h bar omega naught minus 3/2 is equal to n. So then the entropy is equal to KB, the natural log of E over h bar omega naught minus 3/2. And if you wanted to simplify that, you can, but I think that's essentially what they're trying to get at here. So you write an expression for your total energy, and we use that because your microstates can be found with combinatorics, and once you see what that's equal to, then you just solve for it in your energy equation that we have, and then we can plug that into our entropy equation to get an expression for our entropy. So I think that's kind of what we're looking to do here. Hopefully that at least helps or gets you going. And if it did, please like and subscribe. And if you'd like to suggest your own problems, then join my Discord. It's very nice. Everyone helps each other out. It's great.